Welcome back, everyone. We're getting close to the end here. We've got a little more network graph theory type problems to do, um, and then some integer programming, which will be neat. Last night, Canvas was down for like 2.5 or 3 hours. So I sent out an announcement about it last night. Homework 6 is due tonight, if possible. If you had trouble with it, let me know. Um, yeah. I'm going to, since we're delayed on homework 6, I'm going to downsize homework 7 a little bit, and it'll just be um, one one problem on using one of the algorithms that I talk about yesterday or today, or uh, yeah. Um, what else? Hopefully the outage didn't impact anyone's projects. I haven't noticed anything wrong with the Canvas page since it's back up, but if anyone does, let me know. All right. So we've got a shorter lecture today. I'm only going to do one of the problems that's on the schedule, and then I'll do the perfect matching tomorrow, I think, or on the catch-up day maybe. Or the other. There's not going to be a reading quiz for tomorrow. Tomorrow's integer programming stuff. So don't worry about that. Let's just get into the content then. Okay. Minimum weight spanning trees. This is another very common problem, especially in the transportation or communications network type space, distribution as well. Um, it deals with making sure every node on a graph is connected to each other, that there is a path, with but doing that at minimum cost. So if we have a graph, collection of nodes or vertices and edges, a spanning tree is just a subset of edges that touch every node. So here we can see the highlighted red ones that touch every node without any cycles. So to make that a little more clear, we have, in this case, these edges. Every node here is touched by one of these edges, but there's no cycle. So I can't, if I want to get from A to F and then back, I have to backtrack completely. I can't take another route without getting off of the tree. So in this case, this tree is just a single path. In this example, it's a little more general. There is just edges coming off of the root node, maybe E. And there is a path from every node to every other node, but there's only one path from every node to every other node. Notice that if I were to add this edge, per se, now there's a cycle from F, E, D, A to F. And we don't want that in a tree. So a tree is just a collection of edges that's connected to each other that doesn't have any cycles. A spanning tree is one that touches every vertex. Suppose we have weights on the graph on the edge. It's common to talk about the minimum weight spanning tree, often abbreviated MST. And that's the tree which has the same number of vertices, or all the same vertices, and just a subset of the edges, capital E prime, such that the sum of that subset of edges, the sum of their weights, is minimized. And we can see that. Suppose we were laying fiber optic internet cables, and we wanted to connect all of these nodes, all of these neighborhoods, maybe, at minimum cost. Well, we need a spanning tree to do that. We need to find the minimum weight spanning tree across these edges and that will connect all of the nodes, and it will do so at minimal cost. That's one idea of an example. So the earlier examples that I gave they're still spanning trees, but they don't minimize weight necessarily. For example, we can see that 7 here, we could just replace that edge with this edge, and we would lose 2 weight without reducing it from a spanning tree. As an example. Excuse me. So we have a theorem about spanning trees. Okay, well, first of all, Dijkstra's algorithm, which we talked about yesterday for finding shortest paths, does actually find a spanning tree. And in some cases, it can find the minimum spanning tree. If we alter the algorithm, there was a while loop in Dijkstra's algorithm. It said while t is in the unvisited set. Replace that with while the unvisited set is not the empty set. So while there's something in the unvisited set, keep doing that iteration. That's the only change you need to make, and it will find a certain class of minimal spanning tree. We'll find the spanning tree that has its root sort of at the starting vertex, the S. And that's not necessarily the same problem. It sounds very similar. It's usually called the minimal transit problem. It's not always equivalent to the minimal spanning tree, but it's a similar problem, and we already have an algorithm to do that. So, well, let me perhaps explain that here a little better. So Dijkstra's algorithm, suppose we started at C. Suppose C was our initial point. It's going to find the shortest path. Dijkstra's algorithm would find the shortest path from C to everywhere else. And that's not necessarily the same as finding the shortest or the minimal spanning tree. And maybe we'll look at that later after we found some minimal spanning trees and see how Dijkstra's would be different. So here's an important theorem about spanning trees. So we're going to suppose that G is a connected graph with n nodes, and that just means that there are no. Suppose we have a graph that looks like this. This is a disconnected graph because there's a node floating out here, or even a set of nodes floating out here. That there's no path from these nodes back to these nodes. That's a disconnected graph. So a connected graph is one that has a path from every node to every other node. So we're going to suppose that's true about G. And we have a few results. Any subgraph of G with fewer than n-1 edges cannot connect all the nodes. So this is a relatively simple result that we'll show a proof for in a second. Any subgraph with more than n-1 edges must contain a cycle. And any subgraph of G with exactly n-1 edges, which does not any subgraph of G with exactly n-1 edges does not contain a cycle if and only if it is connected. And we'll talk about what this means for our algorithm for this problem in a second. First, I want to show an example to kind of convince you that these are true. So the first idea was that any subgraph with fewer than n-1 edges cannot connect all nodes. So n being the number of vertices, and the subgraph just being a collection of the edges. Here we have 1, 2, 3, 4, 5, 6 nodes, and this path between them is a length 5. This is easy to show perhaps for paths because we can draw a path, and I've drawn it too small. And we can see that between every pair here, there's one edge. So you have 1, 2, 3, 4, 5, 6 nodes in this path, but it only takes 5 edges to connect them. And if we remove any of these edges from our subgraph, suddenly that subgraph is disconnected. If we remove any edges from our path, so if we only had 4 edges in our path, it's not a path anymore, or it doesn't connect all the way from 1 to 6. So we needed, so our tree, so a tree must have at least n minus 1 edges. That's the real result in the context of this problem. Our spanning trees will have at least n minus 1 edges. 2 is similar, and obviously we could swap around these examples. Any subgraph with more than n minus 1 edges must contain a cycle. We notice here that if we add any edge at all to what we already have highlighted, suddenly we can cycle let me do that better. Suddenly we can cycle around. Let's come back to this example. Suppose we had a path like this and we add any sort of edge here. We're going to have a cycle. Let me show you up here. 2 and 5 are connected in G, so there exists an edge here. Suppose we add it there. Suppose we added this edge. Suddenly there's a cycle, right? We can get from 2 to 5 and then straight back to 2. We don't want that in a tree. But adding any edge to this subgraph will induce a cycle. And hopefully you can see that. And maybe you can see how that extends to more general problems. So what this means is, so a tree can have at most n minus 1 edges. Remember that our tree has to connect the graph and not have any cycles. And this should be a spanning tree, because you could make a standard non-spanning tree that has fewer edges. Excuse me. But this one, any tree can have at most n minus 1 edges. And the third statement we had was that a subgraph of G with exactly n minus 1 edges does not contain a cycle if and only if it's connected. So suppose we want to create a cycle here. Let's add this edge like we did before. Now we have n edges. So if we want to maintain that there are exactly n minus 1 edges, we have to remove an edge from the tree. Now we have a cycle, but f is disconnected. And that's just a little demonstration of this principle. So a tree, or a spanning tree, is a subgraph with exactly n minus 1 edges, such that either tree connects all nodes. Or B, let me rephrase that a little bit, such that all nodes are connected, or there are no cycles. If we can maintain either of those conditions, the other one follows. The other one is true. So here it has is stated slightly differently. To create a spanning tree on G, we must merely construct a subgraph of G that has exactly n-1 edges that either does not have a cycle or connects every node. And this gives rise to two different algorithms, two very popular algorithms that we'll discuss and show examples for. There's two different approaches outlined by this corollary. So yeah. First I want to look at the IP formulation for this problem. Xij is 1 if edge ij is in the tree and 0 otherwise. So here we're just minimizing the weight of the tree, and we are selecting at most n-1 edges. And then finally we're gonna, this constraint is commonly used in what's called the traveling salesman problem, which is a very difficult problem. And we'll talk a lot about it in DOR2 and how to deal with it. But this just says that for any subset of edges, or for any subset of vertices in the graph, so 2 to the v is the power set of vertices, it's just the set of every subset, every possible combination of vertices. Power set of v. For every such subset of vertices, we're going to select at most the cardinality, the number of vertices in that set, minus 1 edges. This means that for every subset of vertices, our tree is still a tree on that subset. It may not be a spanning tree on that subset, but it is still a tree. And the problem with this formulation is that it has order 2 to the v constraints, which is again exponential, just like the shortest path problem was. So the IP is very difficult to solve for large problems. Additionally, it's not always a TU matrix. It's not always a totally unimodular matrix. Or the program is not always totally unimodular, so we don't always get integer solutions from a simplex algorithm for this type of problem. We'll talk more about that in DOR2 as well. Like I said, there are two very popular and very fast algorithms for this, and we're going to take a look at both of them. This is Kruskal's algorithm, and we start by ordering the edges by weight. And then we're going to look at the, there should be m edges here. That should be a lowercase m in that subscript. So then for every edge, if that edge does not create a cycle, if we add it to our tree, then add it to the tree. Specifically, we do this in the order that we've weighed them, in weight order. So let's do that real fast. The lowest or the smallest weight edge is A to B, and obviously adding it does not create a cycle. So we add A to B. Then the next smallest weight edge are any of these three, and adding any one of these three will not create a cycle just yet. So I am going to add this edge first, E to F. Again, we have two edges, A to C, B to C. They both cost 4. I'm going to add A to C because I feel like it. Arbitrarily, it doesn't matter. Either will result in a minimal spanning tree. So A to C gets added. Now, our smallest weight edge is B to C, but if we were to add B to C, we would create a cycle in our graph. So we can't do that. Cross that one out. Can't use that edge. The next smallest is A to F. So add him, add that edge, A to F. There's no problems there. And I mistimed the number of things I would need. Slides. So finally, the last edge we add is this C to D. And now we notice that we have added 1, 2, 3, 4, 5 edges, which is our n minus 1 that we're looking for. So we've added n minus 1 edges. So we can stop. So that's Kruskal's algorithm. It takes advantage of the fact that if we don't have any cycles, then we're also going to connect everything. So it takes advantage of the corollary we proved in sort of that direction. Prim's algorithm, on the other hand, specifically tries to connect the graph with this tree. It focuses on the spanning part of the tree. So in this case, we're going to arbitrarily pick a node. I'm going to start with C. So we're going to have U is C. U complement is everything else. A, B, D, E, F. And then we want to, we also have our tree, our edges in the tree. And then we're going to find the smallest edge, or the smallest minimum weight edge that passes from C, or from U, the set. In this case, it's just C. From C to anywhere else in the graph. From U to U complement. In our case, that's any of these edges. So any of the edges in, if you like the notation in the book, pick an edge in delta U. Which is going to be the intersection of V in U delta of V. Forget about that. So the neighborhood of our set U. Well, the smallest edge we can pick here is either of these four. So we have a 6, 4, 9, and 4. Pick either of the 4s. Just to be different, I'm going to pick C to B, because that's not the one we picked last time. Yep. Then we add B to our set U and cross it out of the set U complement. Huh. Why is it not letting me move it? This is awkward. It's not letting me move. Oh, there we go. It's back. So now we have a new U. This is the set U, C and B. So we have to pick the smallest edge that leaves U, which is any of these that I've just highlighted here. The smallest one is clearly B to A, has a weight of 1. So we add that to our edges. Cross out A from U complement, add it to U, and there we go. Sorry if all of my dragging and dropping is a little disorienting. But now we have U is now all of this. So we have to pick from this edge, this edge that connects to E, which is outside the set, this edge, or this edge. Looks like the smallest is this 5 here. So we're going to add A to F. Cross out F from U complement, add it to U, and continue. So U is now all of these nodes. So we could still add E to C, E to F, C to D, or D to A. The smallest one is this 4. So we're going to add E to F. Cross out E, add it to U, and we should only need one more iteration. Because U now contains everything but D, which means we are now looking at the edges which cross into D, which is C to D, A to D, and E to D. Smallest one is C to D, so we're going to add C to D here, cross it out of U complement, and add it to U. And now we're done, because this while loop is while the complement is not empty. It now has no elements. It's now the empty set. and we're done. We found the same, well, not the same tree that we found last time. Um, I made an arbitrary decision that gave us a different tree, but it has the same weight of 4 plus 5 plus 1 is 10, plus 4 plus 6 is 10, is 20. So that's Prim's algorithm, and it leverages that corollary in sort of the opposite direction. It wants to make sure that we have n minus 1 edges that connect every graph, every node. And that implies, by our corollary, that there will be no cycles, and that this will be a tree. Which is neat. Prim's algorithm is very similar to Dijkstra's algorithm in a lot of ways. But maybe the most important is that you can use it's heap sort to reduce its complexity, which is not that important. But both of these algorithms, in the way I've presented them, take number of edges, log number of vertices to complete, at worst. Which is a polynomial time algorithm. Because log is actually sub-polynomial. Again, if you don't understand that, don't worry about it. Just know that these two algorithms are much, much faster than solving the minimum spanning tree with an integer program. So yeah, that's good. That is all the content I have for today, so I will let you guys go.